We've done Laplace and Fourier and continuous time. We're going to get into discrete time transform, and we're going to tie them all together, and you'll see the power of this stuff. Why it's so very powerful. Now, there are a lot of things that we could talk about, but a lot of them, the filters and stuff you're going to get elsewhere, kind of a waste of time in this class. We've had low-pass, high-pass filters, band-pass, band-stop, right? Really what we want to do is talk about how we can use these transforms to design or synthesize, and not just analyze. And I want to get to that as soon as we can. Let's see, I got a couple of properties I want to make sure I underscore the importance of. I didn't get a chance to do this. I've got to get the board first, please. I don't know why this board seems to get so dirty. It does. It's not supposed to rain today, is it?
It is Alabama.
Yeah, well, I hope it doesn't rain. Got a lot of rain. Is anybody in here the period before? Yeah. Do you know what professor has this room?
No. I know they were taking a test in the last one, but so I don't know if it was.
Maybe it's the earlier class. Because this is about as dirty as I've seen it. I don't think they clean it for very long.
The chance of rain is extremely small.
Good. All right. All right, now, let me just get to this. I've talked about the power of reciprocity. A couple of problems I give your homework can only be done through reciprocity, and I'll get to those in a second. But one thing I didn't talk about is, you know, before I said if we have x of t, call it x1 of t, x2 of t here, and we want the transform of that, we know that the transform of that is just x1 of omega times x2 of omega. I can prove that. We talked about that with Laplace, right? Everyone? Now, what? I mean, are you with me on this? If you have two functions multiplied in time, or excuse me, convolved,
Yes.
pardon me, convolved. I'm so sorry. Convolved in time, it's just multiplying the actual bulb is still on a projector bulb. All right, now, if you have, and this is convolution, it's not shown very well, but if I have x1 of t convolved with x2 of t, it's just multiplying the transforms of x1 and x2 together in the frequency domain to get the product. Follow me, class? It's the same thing with Laplace, remember? x1 of t, x2 of t, you get x1 of s times x2 of s. I mean, if you get convolution in time, it's multiplication of frequency. It's the same here. Now, this other property is an important one. If we have multiplication in time, x1 of t here times x2 of t, then we get 1 over 2 pi times x1 of omega convolved with x2 of omega. This one isn't real apparent. Follow me on this? There's a 1 over 2 pi here. Are you with me? Class? Y'all see this property in your book if you look there? You got x1, x2 there. It's multiplying two functions in time. And the frequency domain, you have to take 1 over 2 pi and then you convolve the transforms. It seems like a more difficult way to do it. But think about this. Convolution is relatively trivial if you have delta functions, right? If you had a delta of omega, do you agree with that? Or if you have just a square block, because blocks can move through each other very easily. Do you agree with that also? Like pulses. Agreed, class? It's easy to convolve pulses. So keep that in mind. This is not generally easy, but there are special cases when it's very easy, and you need to be aware of this. Also, you need to be aware of this for more general reasons, because when you do a lot of design work and synthesis, these properties will become very important. So keep that in mind. Now, that's the first thing I had to say. I'm going to apply that to a problem in the homework after, if it's not the one you're asking in a second. The other thing I want to talk about is energy in signals. Whenever we talk about energy in signals, in general, energy, the symbol is E, believe it or not. E, it's script E. We're talking about something that has an infinite duration in time. Energy, you can't say energy per unit of time would be power, but the energy in a signal is something that the signal is, the duration could go on to infinity. It doesn't have to. There's a certain finite energy. Now, energy is power integrated over time. So if you think about total energy, it would be the integral from minus infinity to infinity of whatever the power was in a signal, dt. The way we do this in signals and systems, when we talk about the power or energy in a signal x of t, the way you can interpret it is you can assume x of t is a voltage. And you can assume it's going to be driving a 1 ohm resistance. All right? Now, you just have to accept that. This is the way it works. The definition of energy in signals and systems assumes this. A lot of you are based heavily in physics. That's the way I am. When I hear energy, I think about something that can do work where it's measurable, energy in joules kind of deal. Here it's more abstract. So to make it real to you, think of a voltage being the signal x of t that you want the energy in, and it's driving, the voltage will be across a 1 ohm resistor. Do you follow me, class? So it's V squared over R. If R is 1, it's just V squared. Do you agree with me? Therefore, energy for us will be the integral from minus infinity to infinity of simply, well, it would be the power. If we assume we have a resistor of 1 ohm, I'll make it real to you here. Let's say I have 1 ohm here, and now I have a voltage here, x of t, right? Follow me? Got a voltage x of t across 1 ohm. Well, you could say that the current flowing through there would be x of t over 1. You can multiply voltage times current, x of t times literally x of t, and get the power. Do you agree with me? So the power would be x of t squared. I'm going to put a magnitude here just to be for a reason that sometimes they try to make this a complex number, which I don't like, but they do. It's the magnitude of x of t squared dt. That's the energy, and that makes sense. It's the way it was in physics. Assuming you had a 1 ohm resistor and x of t was the voltage. Do y'all give me that? So let's take a look at an energy in the signal, and then I'm going to show you a theorem. Well, this is the energy in a signal. This is one way to get it. Let me go the second way. Now, you can also show this. I'm not going to prove this one, but it's relatively trivial to do. You all know that I could say that x of t right there is 1 over 2 pi, the integral of x of omega times e to the j omega t d omega. That's how I could define it from the inverse Fourier transform. Are you with me? I could take that, stick it in there, then take the magnitude of that and square it. Take the magnitude and square it, and the result is this. It's equal to this. I don't want to fuss with this too much. You could say that energy is also 1 over 2 pi, the integral from minus infinity to infinity of x of omega magnitude squared d omega. Either one of these two will get you the energy in a signal. Understand? This has the transform. You happen to have a transform. This is the actual signal. And either one will get you the energy. All right, class? Now, if you think about it, suppose I had a sinc function in time. Just go with me on this, all right? A sinc function in time. I know that transforms into a pulse in the frequency domain, right? Isn't it easy to integrate a pulse? If you just have a value of some constant over some range of frequency, right? It's the constant squared times whatever the range of frequency to get that. And then you divide by 2 pi. How many agree with me there? Or, it beats the heck out of integrating a sinc function, squaring it, and God knows what kind of crazy stuff can come out of it. I'm just leveling with you. I'm a professor. I would never do that. Not unless I had a gun to my head and had to, because that stuff wastes time. An integral of a pulse in the frequency domain doesn't waste time. It's trivial. I'm going to give you one clear example, because I know if I'm where you are, I'm wondering, well, show me something that's how that could be. So here's one. We'll see which domain we want to work in to get energy, all right? Now, I know that if I have a pulse function, p tau of t, in time, that goes to what? Tau, right? Times the sinc of omega tau over 2 in the frequency domain. Does everybody give me that? Right? It's trivial. You've got to know this. I mean, this is like, if you don't know this, you're really in so much trouble you don't even know. Then you come here. Now we're going to use reciprocity. So I take tau here, and I take the sinc, right? Now, not omega, but t tau over 2 here. And based on duality, what do I put over here for my transform? People? Right. That's right. 2 pi, keep going. Exactly. Right, and it would be minus omega, but can it be plus omega?
Yes.
Why? You're right. Anyway. Even, right? It's an even function. So we can just make this. Now I'm going to tell you this much. I'm going to get rid of I'm going to take the 2 pi over here, so we'll make that nice. This is 2 pi. You'll see why this is important now, I think. All right. So here.
Probably an Amber Alert.
It's presidential alert.
All right. Unless whoever attacked, ignore it.
Well,
It says it's
What is it?
it was a test.
Pest. Oh, that was nice.
There's a distraction.
So now I say, I give you a problem. What?
Why did you divide that?
Remember what? There was 2 pi here, right? Divide both sides by 2 pi.
Why?
Because when I come from here to here, there's what? I go 2 pi, right? And then it's p of tau, then p becomes minus omega, right? For duality, but we don't need a minus because it's an even function. This is just duality, people. Do y'all, how many see this right here? Guys are with me? Now, listen, here's a typical Baginski problem. If you're paying attention here, you'll see this. Trust me, I'm giving a test away. If I say this is x of t, and I won't show you that, and I say I want the energy in that signal. Now, what happens is the people that do it by brute force and awkwardness are going to take this and square it, and then try and integrate it dt from minus infinity to infinity. And God knows what they're going to come up with. I mean, it's always fun watching, but it's wrong. You follow me? Isn't that a pain right there? Take that and square it, and then go ahead and integrate it. Well, some people say, well, that's really, I know that sine of tau t over 2 divided by tau t over 2, so I'm clever, I got that. Then I have to square that and come up with some god-awful way to integrate it. Good luck. It'll take you a while. It'll take me a while, and I've done that. I don't want to do it. But that one, that magnitude is a pulse, right? Agreed? What's that magnitude squared? 1 squared is? 1. It exists from minus tau over 2 to tau over 2, right? Let's get the energy in this. I hope this is making it clear. I don't know, the moral of the story is don't integrate stupid stuff. I mean, don't integrate things that cause you pain if you can do it very easily in the other frequency domain to get the energy. So let's just do it over here. We're not going to do it this way. We're going to go over here. We can say the energy in that signal is 1 over 2 pi, right? And it's just the pulse squared, which is just 1, from minus where? From minus tau over 2 to tau over 2. The magnitude here is just 1. I could scale it up and make it A and then put A over here, couldn't I? Do you agree with me, class? You all see how easy this is? Now, if I take this 1, right? The reason I didn't just put a pulse there, because I know the coefficient's 1. 1 squared is 1. It exists from minus tau over 2 to tau over 2 in the omega domain. Do you agree with that, class? Isn't that right? How many see it's so obvious? Y'all with me? It's so obvious. Then I just do what? D omega, correct? What's the answer? Look at that. 1 over 2 pi times tau. Voila. Trivial. But on tests, I'll see that squared and integrated for no reason, because they didn't realize the whole point of that theorem was so you don't have to do the hard part right there. Understand, class? How many see that? Now, some of them, it really doesn't matter. Some of them are so easy. If I say x of t here, I want the energy in this signal. Listen, I'm going to say my x of t is this. I want the energy in this signal. X of t is e to the minus 2t u of t. I want the energy in the signal. How do you want to do it? Well, what's the transform of this, people? 1 over 2 plus j omega. Isn't it, class? How many see that? Right? All right, now, you could take the magnitude of that, couldn't you? The magnitude would be what? 1 over quantity, it would be magnitude squared, wouldn't it? So it would be 1 over 2 squared plus omega squared, right? Trust me, right? Then you would have to take that d omega. You could do that one. That's not too bad. Or you could just take this and square it, right? Remember, once you did that integral, you took the magnitude of this and squared, you have to do the integral from minus infinity to plus infinity. You still have to multiply by 1 over 2 pi, right? Let me just put it to you this way. If I look at this and I want the energy in the signal, this is the time domain, this is the frequency domain. I'm going to show you what you get both ways. In the time domain, it would be the integral of the magnitude of e to the minus 2t squared dt from 0 to infinity, which would be equal to 1 over 2 pi, the integral from minus infinity to infinity, of 1 over 4 plus omega squared d omega. Now, which one of these two do you want to do to get the energy? Both will give it to you. Probably this one. I agree with you. Why? Because that's just e to the what? Minus 4t. Isn't it, class? You all see that? E to the minus 2t times e to the minus 2t is e to the minus 4t. Do you agree? So I could replace this as e to the minus 4t. And now, do the integral on that side. This would be the energy here. What is it? Well, e to the minus 4t dt. Integrated is, say it, class, 1 over minus 4, correct? Times e to the minus 4t evaluated from 0 to infinity, right? What do I do? If I have a minus 4 downstairs, isn't that same thing with a minus sign in front of this whole thing, class? And what do I do when I see a minus sign there? And I got limits?
Flip.
Flip them, yeah. Make this 0, make this infinity. What do you see? 1/4, right, times e to the 0 is 1 minus e to the minus infinity is 4, simply 1/4. Agree? That would be the energy in that second. This one may be a little rougher. You can do it, right? But it would take a little more time. How many agree with that? Are you with me? You have a variable change here. You have what? 4 plus omega squared would be u squared. Do you agree with that? You'd basically manipulate it so you get 1 over some quantity, like a u squared du. And then you could do it. Agree, class? But this one would take a little more time. That's an easy way to do that. Follow me? So be aware of that. That's why that theorem is so powerful. It makes your life easy if you know what the transform theorems are. And anytime, like just think about it. You know, you're smart people. Anytime in any domain you've got a delta function, that integration is a gimme. Do you agree with that? Right? Anytime you have a pulse of finite width, that's a gimme too. Keep that in mind. Those are the two biggies when we're talking about energy. Okay? I want to make sure you all see that. Yes, sir.
Quick question. So whenever it says e to the, when you have the integral of 0 to infinity, e to the negative 4 to the dt, it's not u of t because you have...
Well, u of t starts at 0.
Yeah,
That's it. That's the reason I put u of t there, right? If I want to start at minus infinity, then I would have to have done this to make it actually legit, put absolute value over the t. So the t would always be, the quantity here would be something positive, right? And the minus 4 in front of it would cause it to decay. I don't want to mess with that. All right, class? Yes, sir?
Real quick. So when you do the transform and then you try and take energy, do you have 1 over 2 pi out front?
Yeah, right here.
So for the first example you did with the duality thing, when you took out 1 over 2 pi, would you still have the 1 over 2 pi for the other integral?
When I do this integral right here, when I take this quantity and square it, I'm looking at the energy in the signal, and I'm saying this is the time domain signal. The tau over 2 pi is there.
Okay.
All right, I'm saying that's it. Because I didn't want to scale this. That's the reason. I could scale and make it 2 pi over tau here, but I didn't want to do that. Follow me? So I could do that, but it really, I'm trying to focus on that point of make the easy integral choice, always. Don't be dumb. I have done dumb things with integrations, and sometimes I think, well, I'm gonna just do it because I can do it. I'm gonna show myself. Waste of time, magnificent waste of time. All right, hope I made that point clear. And you'll see later in your coursework, this is gonna be really valuable. And some profs, and I've had a prof like this, they wait until you learn the lesson the hard way, painfully. They don't tell you the trick. And I don't like that at all. I'm not saying it out there. Now, oh yeah, now we're talking about one other thing. Now, I'm going to tell you this. I said first off that Fourier transforms were for energy signals, right? Signals that had a finite amount of energy, correct, class? They didn't, in other words, you couldn't take a Fourier transform of a cosine theoretically. It has an infinite amount of energy. Do you with me on this? Because it exists forever. However, I want to tell you this. There are things, this is called the general, the general Fourier transform theory of the technique. And I'm going to show you what I mean by it. Now, here's the one thing I really want to underscore. When we're talking about frequency domain techniques, mainly Fourier transform techniques, what they allow you to do as engineers is take a peek into the frequency domain and see what's going to exist there if you're an engineer. So, for instance, if you have a cosine waveform, you know when you do the infinite series of that in terms of the exponentials, really what you get is what? You get one single frequency that's going to be there. I know it's at plus or minus omega naught, but frankly, it's at omega naught. That's where all the energy and power is. Follow me, class? So if you took a spectrum analyzer, which looks at the frequency domain, in an area where you had an antenna radiating a cosine of omega naught t, or a sine of omega naught t, either one, or any combination, then you would see all the energy, you would see nothing, then you would see a spike, then nothing, right? And you would have all your energy at omega naught. Got me on that one? Now, if you have something like a repetitive periodic square wave, then you're going to get energy at every single harmonic, at omega naught, 2 omega naught, 3 omega naught, but it will be monotonically decreasing strengths or amounts of energy. Are you with me, class? And the energy really, I should say power, if it's periodic. All right? Now here's one way of looking at a lot of the energy in periodic signals. And I'm going to show you. Remember we said for any periodic, I said this, for any periodic signal, I can say x of t was equal to the summation from n equals minus infinity to infinity of some c of n e to the j n omega naught t. Y'all give me that. Y'all remember that? Now I'm going to show you something. We're going to take a look at the energy per unit. You might say the energy, really the power, in each frequency component. Now I want you to watch this just for a second. This is actually important. Think about this. Let's start here. I'm going to say if I have to do the old x of t on this side, x of omega on this side, and work with me. If I have 1 here of x of t, remember that's on forever, from minus infinity to plus infinity. It's a DC kind of value. What's the transform of that anyone? You know it's going to be 2 pi delta of omega. We got that with duality, didn't we, class? All right, keep listening. Now, I want you to just think about this. Suppose I think of this x of t right, or this thing, as my x of t that I'm going to be talking about in this column. Now what happens if I have x of t times e to the j omega t? Make it omega naught t. What happens over here? What does that do? Do you remember? Anybody? It takes this transform and does what to it? It would take x of omega minus omega naught, correct? Now you'll notice, but my x of t was 1, so what would it do? Now it would be 2 pi, right? Times delta of omega minus omega naught. Do you agree with that? You all see that? I'm calling my x of t 1. I can do that. With me? Keep going on this. Can you guys see in the back there? All right. Now what happens if I have x of t times e to the j n omega naught t? Anyone? In the back. Can you get that one? Just do the analogy. What changed? I don't have omega naught, I have an omega naught. What do you think's going to happen? Wherever I have omega naught, it becomes an omega naught, right? So now it's 2 pi times delta of omega minus n omega naught. Got me on that, class? Are you with me? Jeff, can you see what I'm writing or not? Almost. All right, I'll write bigger. Whenever you start squinting like that, it scares me. Is it that bad? I don't know. Can you see it right there? You can, maybe. I need to write bigger. Now watch. I'm going to take the Fourier transform of this signal. Got it? All right. Based on what I just know. So now I take the Fourier transform of this thing. When we take the Fourier transform, call it, I guess, script f of x of t here. Now what am I going to get? Well, I'm going to get that summation, right, of n equals minus infinity to infinity. Leave Cn alone. That's just a magnitude of phase, isn't it? It's a scalar, in other words, right? C of n equals 1 has a certain magnitude of phase. Never changes in time, correct? That changes in time. And what do you get? Now it's going to be 2 pi times delta of omega minus n omega naught. And now let me talk about this for a second. This is in the frequency domain. You understand that? And this is what you would literally observe with a spectrum analyzer. Spectrum analyzer, I assume you know this, but in case you don't, it allows you, you can put an antenna up, and the antenna will measure the input waveform, and it will find, the spectrum analyzer will locate the amount of energy at each specific frequency, or the amount of power, all right? And then it registers that with a line. What you really see with the spectrum analyzer, if you looked, would be this. You would see there's some kind of a noise floor that's always there. And then, if you had a periodic signal, say this was a square wave, and you see event values with the coefficients for a square wave, then you would see at omega naught right here. At the fundamental, you would see this thing jump up, just bounce up. Then at 2 omega naught here, it would bounce up a little less. At 3 omega naught, a little less. And it would asymptotically go down, and these values would be the magnitude of that C of n. See that, class? Are you with me? I mean, this isn't the power right here yet. Technically, I have to take this and square it, so it would be the square of C of n times 2 pi. But what I'm really getting at, without spending too much time on this allows us to peek into the frequency spectrum and see where the signal strength is. That's what we can do it. That's what Fourier analysis allows us to do. So that's the way you view this. Okay, class? All right.
You're right, she was untied, so just be careful.
I know. I can tell. You'll see the power of a lot of this stuff in later courses, but you have to be exposed to it now. Next, after that, I've got a few other, now I'll take your questions about the homework. I've covered, that's the last thing I need to cover, the Fourier stuff. Go ahead.
So sine pi over
I know that one. Here, let me give myself more of the board. I know where you're going with this. By the way, how would you do it based on what we've talked about so far? It's pretty easy now. I'll put it up there. I know what it is. It's really not quite that easy. But I say over here I have what? Sine of pi t over pi t, right? That's a sine times sine of, go ahead, 2 pi t over pi t?
Yes.
Over pi t. Do I want that as pi t? Class? I want it as 2 pi t so I can make it a sink, right? Agree? So I'm going to put a 2 here, and then I'll put a 2 here. Agree? Now look, you all agree with this first one right here is a sink? Right? And you all agree that this is a sink? Right? Come on, right?
Yep.
All right, so what am I going to do? I'm going to say that this is really 2 times the sink, right? S-I-N-C of pi t times the sink, right? Of 2 pi t. That's S-I-N-C. They're both sink 2 pi t, correct? and I want the transform of that. You'll notice they're multiplied, correct? So let's first say what we're going to do. If I have x1 times x2 times, and the frequency domain, it's 1 over 2 pi times x1 of omega convolved with x2 of omega, right? So now, first of all, I'm going to say my x1 of omega, or x1 of t, will be the sine, sinc, pardon me. This is going to be equal to the sinc of pi t, right? Now, listen to me, so we can be together on this, make sure. And I want to make sure that you guys are with me. How many got this one? I think they got it at least. I figured at least a third of the class got it, whether you admit it or not.
How does the second sync become sync of 2 pi t at the top?
What did I do? There was a pi t down here, right? So I multiplied top and bottom by 2. That way I can get 2 pi, oh, sorry, isn't that 2, this is 2 pi. That's 2 pi t, right? Class? Okay. Now look, now I'm going to do the duality thing again. I know pulse tau of t goes to tau times sinc of omega tau over 2, and down this way, tau times the sinc of t tau over 2 goes to 2 pi times pulse of minus omega, or because it's even omega, right? Now, I'm going to go ahead and, since what's the coefficients of those sincs? 1. Since the coefficients of the sinc are 1, I'll divide this by t over here, right? That way, what I want is, I want to make sure I just have sinc there. Nothing in front of it. Got it, class? With me? How many are with me right here? Can you see it right there? I mean, can you see it? I want to make sure that I'm not losing something. Now, what am I going to do? I got to get the coefficient tau over 2, right? Let's be specific. What is it now if my sinc function is the sinc of pi t, right? Well, then pi would be tau over 2, correct? Right? That's the coefficient of t. So if pi is tau over 2, then 2 pi would be tau. Do you agree? Agree? So what would the transform be? It would be 2 pi over 2 pi times the pulse, right? Here, I'll put it down. Tau for this one is 2 pi, right? And that's going to be this as a width of 2 pi of omega. Agreed, class? Right with me? And that goes away. Agreed?
Did you multiply it?
How do I get what? Help me. Here?
Right there.
This?
Yeah.
Well, that is the coefficient of 1, right? All right, that means tau over 2 has to be pi, because it's the coefficient of t, right? So if tau over 2 is pi, tau is 2 pi, right? And then I came over here, and remember I had 2 pi over tau, that means it's 2 pi over 2 pi or 1. All right? It's straightforward. I'm not doing anything tricky here at all. This is trust me, this is an easy one. Now, come in here, you look at this, right? I have this relationship. That sinc function goes to that. Agreed, everyone? What does the next sinc function go to? Now, if I have sinc of 2 pi t, right? What does that go to? Look at the most basic form of this relationship. The coefficient in front of there is 1. Is it not, class? Now, what does that mean? That means the coefficient of t here, tau over 2, is now 2 pi, isn't it? Right? Look at the coefficient of t, it's 2 pi. That's tau over 2, right? That means tau is 4 pi for this one. Agreed, class? Tau equals 4 pi. Agreed? There's nothing tricky here, it's very honest. Now what happens over here? If tau is 4 pi, I come up here and I have 2 pi over 4 pi, or a half. Agreed? So now I have this as 1/2 times p. What's the pulse width? 4 pi. Of omega, correct? Can you see it back there? I know I'm a little slow on this one, but yeah. Look, what's the coefficient? Isn't the sink of 2 pi t, right? Well, what is 2 pi? Isn't that tau over 2? It's the coefficient of t in there, right? What's the if tau over 2 is 2 pi, what is tau? 4 pi. Here, I'll write it down for you. If tau over 2 equals 2 pi, tau must be 4 pi. That's it. I mean, there's nothing tricky. This is all this is it gets. So now I have the sink here and the sink here and the transforms, correct? Agreed? Work with me, guys. Now, come over here. Let's go back to the original. I have these two multiplied, right? And we know if I have, and I'll do it here, if I have x1 of t times x2 of t, this is the original property I put up there, that's in the frequency domain, 1 over 2 pi x1 of omega times x2 of omega. Isn't it, class? This is convolved. Pardon me. This is convolved. I'm sorry, I'm getting in a hurry. Forgive me, class. I will slow down. Are you with me, class? Multiplication in time, convolution in the frequency domain. Guys, are you with me? Now, if you take one look at this, let's just talk about this. I'm going to take, I've got the transform of these things, so now I have 2 times 1 over 2 pi, and then it's going to be what? The first function, which is p of 2 pi of omega convolved with the second function. That's p of 4 pi, right, of omega, but this one has a half in front of it, which means this 2 can go away. Agreed, class? How many see this, right? Now, if you're convolving these two functions, isn't that a pulse? And isn't this a pulse? Remember, aren't they both pulses? What happens when you get pulses convolved together?
Triangle.
You're going to get triangles out of it. It's a very, can you do that one? If you convolve two pulses like that, what happens? How about we leave the 4 pi alone? If we're going to convolve the two, let me just do it this way. Here's the first one. I can't use omega, I'll use, so now we're going to have p of 4 pi of tau. That one I'm not going to shift. It starts at minus 2 pi and it exists till 2 pi, right? I want to convolve that with another function. And that's p of 2 pi omega, right? P of 2 pi omega, if I make it, now I'm going to replace omega with minus lambda. Remember with convolution, you got to replace it with minus lambda. It looks the same, doesn't it? It's an even function. So this one doesn't even, when I flip it, it doesn't, it's the same thing. But then I shift it, don't I? How far do I have to shift it? Originally, when I flip it, it looks like this. This would be, sorry, it looks like this. It would go down to minus pi here, up to pi here. It would have a height here. I'm making both of these 1 because they are both 1. I'll take the 2 pi out in front at the end. Now this is going to be my second function, p of 2 pi of minus tau, right? And now I've got to shift it down. Instead of t, I use omega. So now I'm going to move it down. And how far down am I going to move it?
Omega is negative.
That's right. Now I'm going to move it down what?
3 pi.
Until this starts exactly 3 pi. Whoever said that. So now I have to go all the way down. It's going to look like this. That's 2 pi, right? Or minus 2 pi. The width of that is 2 pi. This is minus 4 pi, right? I've shifted it by 3 pi. Understand the center? Now, that means this entire function is going to start at minus 3 pi, right? And it will go to plus 3 pi. You'll notice the span is 6 pi. What do we know if we can convolve two functions? The total width would be the width of the first plus the width of the second. 4 pi and 2 pi is 6 pi. Understand, class? So you start at minus 3 pi. And this is p of 2 pi of, it's actually minus 3 pi minus this. That's what the actual argument would be right here. But bear with me. Now look what happens as I move through here. You see how you're basically going to get overlap here to here to here to here to here. And then it's going to stop where? when I go from minus 3 pi to minus pi. You with me? And then this pulse will be immersed in this pulse. And then it'll be flat for a while. And then after I hit one, that's going to go from minus 3 pi to minus pi, and from minus pi to plus pi, it's flat. And then from plus pi to 3 pi, it drops down. Here's what it'll look like. I spent so much time on this. There's one thing I got to do today, but I know this is a good one. I'll give you the answer to this one. Here's what it'll look like. The final convolution, when all is said and done. Starts at minus 3 pi, ends at 3 pi. From minus 3 pi to minus pi, it's doing this. Then it's flat all the way through here until you hit pi here. And then it's flat, it does that. And the magnitude here is this area right here, which is going to be 4 pi. So the area here is 4 pi, right there. And that just goes to 0 through pi. Understand, class? That's the way it looks. Now, what's nice about this, now that I have this right here, that's the Fourier transform of that, isn't it? That's what our goal was, wasn't it, class? Agree? And I got there using duality, and then knowing multiplication of time is really convolution of the frequency domain with the 1 over 2 pi in front of it. And that's what it looks like. So this is the convolution of these two. And you have to divide by 2 pi. So the actual height here is 2. All right, I'm trying to fly through this. I've got about 2 minutes, don't I, roughly? I started a few minutes late. Now, let me get to this part. That's where I was going. I hope I answered your question. This problem right here is based on one thing, an understanding of duality. And then messing around with convolution. But the convolution isn't really that hard. It wasn't a hard one. If you sit down and do it tonight, you'll see it's easy. It's hard right now if you haven't taken a stab at it, but it's a very easy problem once you mess with it. How many did this one and got something like that? One? No?
I tried it. I didn't think you
Francesca, texting me. You know this one. A couple other people I know this very well. And I can tell the way they talk to me about it. But I know some others are struggling, mainly because probably you haven't committed enough time to this stuff. It takes a lot of time. I'm taking up the speed and making this flow. It's easy. Boy, it takes a lot of time at first. Now, next thing I'm going to show you is we talked about Fourier transforms, right? We talked about first Fourier series and Fourier transforms, right? Now we're going to go and say that we're really going with this, and you know this as engineers, everything now is digital. It's sampled, right? Everything is sampled, and then it's discretized and stuck into values, singular values. Jeff knows more about this than I do. I can almost guarantee it. That's his world. Anyway, so now I take a signal x of t, but now I'm going to say, I'm going to sample it. So I'll put a sub s here, and now I'm going to say this represents a sampled signal. We're going to only take values at discrete points in time separated. Well, how to do that? You'll love this. Maybe you won't. So now I'm going to go ahead and say I'll take the original signal x of t that I'm going to be messing with doing a Fourier transform, and I'll sample. What do you think is the best thing to multiply that by if I want to sample? Take a guess. Of all the functional things in the world to do, what would you multiply it by? A delta function, exactly. It's going to be a delta function spaced at t minus nts. Now, nts would be the periodicity, how long between samples. So I have a waveform that looks like in the time domain like this, and now I'm sampling it at discrete points, right? All through here. Here, 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 all spaced by TS. And these are the values I retain in the sampled signal. Follow me? How many see that? The delta function allows me to do it. The delta function will irritate you. It's the Dr. Baginski has an infinite value. How can you get an infinite value sampling times? We're going to get there. For now, this is the easiest way for me to go. All right? Now, the next thing I'm going to do is say, well, if I sample that signal, now I want the Fourier series, Fourier transform. Give me 2 minutes, I'll make it up to you, all right? I'll owe you on this one. So how do I get it? Now I can say my x of omega technically is equal to the integral from minus infinity to infinity of x of t, but now it's this. Now it's this crazy sum. from n equals minus infinity to infinity, I'm not gonna put x of t in there, I put my x of s, it's sampled, and I put x of, now this is gonna be x of nts, because this will only have a value when this turns on, times the delta function of t minus nts, it's that times, I'm almost done, guys, e to the minus j omega t dt. Now that is the exact definition of the Fourier transform, but instead of putting x of t here, I put the sample signal, got it? Can you see it back there, you looking like?
The n equals, is that minus infinity to?
Infinity.
Okay.
It's an infinite series of delta functions, all spaced by ts. ts is really the sampling period. How, spacing and time between samples. Now, if you look at this for a second, the reason I put NTS here is this. This only is going to have a value that concerns us when this delta function turns on. And it only turns on when t is NTS, right? Now watch. Now when I integrate a delta function, listen, this is an integral, right? It's with respect to dt. When I integrate this delta function, really what I'm doing is just extracting the values of this function when the delta turns on, or an NTS. Just let me finish it. I'm almost ready to let you guys free. And now I can say I have x of nts times e to the minus j omega nts. So now instead of an integration, I have a summation. And the values here are really the values of x at specific instances in time, NTS, TS, 2TS, 3TS, and so forth. Now, as a general rule, we don't put the TS here. That sampling interval is never stated. Write this down. What this is normally going to be given us, and this is called the discrete time Fourier transform, that's what I'm going to pick it up next time. It's equal to this, the summation from n equals minus infinity to infinity of x, and then they put a square bracket of n. Now they suppress the TS. They don't care about that. It's something that can be stated outside the definition. And it's times e to the minus j, but now instead of omega n or TS, now they just put capital omega here, and then times n. They put, so really capital omega here is equal to omega times TS. And this is the definition right here of the DTFT. I didn't have time to do any examples. I'm going to give you some reading and some very simple problems. And then we're going to pick it up there. And now we're in the sample domain. We're going places. That series is still infinite. Not very useful at first, but it will be. Yes?
We had a test Monday before we not have a credit card.
That's correct. But we can be here Friday. All right? And I'm going to give you some homework with respect to this. And with respect to the question, is this on the test? No. Does this make sense to you what I'm doing here? Sorry I spent so much time on that problem. I'm happy to be interviewing because that's so important. Francesca, have you had one?
I did until now.